9.4, the intersection of three planes. So we're going to take a look at consistent systems for three equations representing three planes. Okay, so when we have three planes and we want to take a look at how they intersect or even how they don't intersect, there are different cases as well. So case number one, there is one point of intersection. Okay, we can see this in the corner of our room. If we look at one wall and is connected to another wall and then is connected, those both are connected to the floor, we can see that they all intersect at one point. Okay, the two walls have a line of intersection. The floor in one wall has a line of intersection. Floor in the other wall has, again, a line of intersection. But when you put them all three of these together, they intersect at a single point. What we need to remember about these is that their normals are not scalar multiples of one another. Okay, case two, three planes can also intersect in a line. So you can have a line of intersection. Okay, so they can just pretty much cut one another and all intersect at that line in the middle. In this case, there's an infinite number of solutions in the form of an equation of a line. Okay, so for case one, we're going to get a single point, x, y, z. For case two, we're going to get an equation of a line. Okay, x, y, z plus t, a, b, c, for example. That's like the vector form. Okay, and please note that in this case as well, all of the normals are not scalar multiples of one another. Okay, case three. So case three is also a line of intersection, but this time, what happens is that two planes lie right on top of one another. Okay, so pi 1 and pi 2, two planes have the exact same equation. In this case, those two planes, their normals are scalar multiples of one another. And then, of course, also their d value will be a scalar multiple of one another. Okay? The same scalar multiple. However, the other plane, that plane cuts planes 1 and 2, so that plane does not have a normal that's a scalar multiple of the first two planes. And our solution is going to be a line. So again, we have a line of intersection and we have an infinite number of solutions. The solutions are going to be in the form of the equation of that line. Okay, in case four, a plane of intersection. If all three planes lie on top of one another, what happens is the entire equation of the plane is going to be the solution. So where those three planes intersect, it's going to intersect at every single point possible on that plane. So all three normals are scalar multiples of one another, and then all three d values are scalar multiples of one another, and again, the same scalar multiple. That's important. Okay. In other words, the three planes have identical equations. Okay, and then this is where those elementary operations are going to come into play and be very, very important. Okay, so we're going to determine the intersection of the three planes with these equations. So what I'm going to do is I'm going to rewrite these in a matrix. So 1, negative 1, 1, negative 2. 1, negative 1, 1, equal sign, negative 2. 2, negative 1, negative 2. Then we have negative 9. 3, 1, negative 1, negative 2. 3, 1, negative 1, negative 2. Okay, so I'm going to, in the next line, I'm going to rewrite equation 1 as it is. And what I'm going to do is I'm going to take row 2 and subtract 2 of row 1. And I'm going to take row 3 and subtract 3 of row 1. And sorry, I missed this. I just want to point out that the normals, and sometimes when we look at it, we take it for granted because we glance at it so quickly and then we just know. As soon as you're really, really deep into math, we just know. So if we take a look at the normals, they're clearly not scalar multiples of one another. Okay, so n1 does not equal some constant, n2 does not equal some constant, and Okay, and this is actually what's telling us that we need to put these equations or these numbers into a matrix and then go from there. Okay, so back to this. R2 minus 2 of R1. So 2 minus 2 is 0. Okay, that's our goal. Our goal is to take this triangle and make as many zeros in this triangle as possible. Okay, -1 minus, and then that would be -2. So that's, in other words, is -1 plus 2, I get 1. And -2 minus 2, I get -4. -9 minus, and that would become -4. So -9 plus 4, I get -5. Okay, next one. Row 3 minus 3 of R1. So 3 minus 3 is 0. 1 minus -3, in other words, 1 plus 3, I get 4. -1 minus 3, I get -4. And then I have -2 minus -6. So -2 plus 6, I get 4. Wow, row 3 is actually quite pretty. I'm just going to divide row 3 divided by, by 4. Okay, so we're going to get 1, -1, and 1. So 1, -1, 1. Okay, the first row hasn't changed at all. 0, 1, -4, -5. And then we can reduce that to 0, 1, -1, and 1, which looks a lot better because now we can take row 3 and we can subtract row 2. Okay, this time it actually works. I think that this is the first question that we've went over where this actually works, where 0 minus 0 is still going to give us 0. Okay, so 0 minus 0 is 0. 1 minus 1. -1 minus -4. And then 1 minus -5, so I get 6. And again, R3, I'm actually going to divide by 3. And I don't know why I put a 0 there. Sorry, it's 1. 1, -1, 1. And this is going to be our final matrix. We're not going to have to do any more. Oops, divided by 3. All right, so we were able to achieve this triangle of zeros. That means there's a point of intersection. And now what we're going to do is we are going to solve for this point. So we know that the first column represents the x values, the second column represents the y values, and the third column represents the z values. So this equation right here is z equals 2. That one's done. Okay, row 2, the equation is y minus 4z equals -5. In other words, y minus 4,2 equals -5. Y minus 8 equals -5. Okay, bring the 8 over, it becomes positive 8. I get y equals 3. Okay, and then row 1, we can rewrite row 1 as basically the original up here. X minus y plus z equals -2. Now we can just sub in x minus 3 plus 2 equals -2. Okay, -3 plus 2 is -1. Bring that over, it becomes +1. X equals -1. Okay, therefore, the point of intersection is -1, 3, 2. Example 2. Determine the solution to the following system of equations. So again, we have 3 unknowns, 3 equations. So first, let's actually not forget this. Let's check the normals. We have 2, -1, 1. Okay, we have normal 2, which is 3, -5, 4. And then we have normal 3, which is 3, 2, -1. Okay, so I don't believe, 2 times 1.5 is 3. Okay, no, so n1 does not equal a scalar multiple of n2, does not equal a scalar multiple of n3, So we should get a point of intersection. So let's go ahead and write these out in a matrix. 2, negative 1, 1, 1. 2, negative 1, 1, equal sign, 1. 3, negative 5, 4. 3, 2, negative 1. Okay, so this one's a little bit harder because we don't have that equation that just has like all ones in it. Okay, so I might do this a different way. I might show you guys, instead of having these three, this corner here as all zeros, we basically need to get a 0 in one of these equations and then 2 zeros in another one of the equations. So it may not work out to be in that corner. That corner is just like a guideline. So let's see if we can play with this. Okay, what I like about the first equation here is that they have all, except for the x value, these three are just simply ones. So let's go ahead and take row 2 and let's subtract, let's go 4 of row 1. What that's going to do is that's going to give us a 0 in this position. Let's see what happens. All right, so 3 minus 8, I get negative 5. You know what? I do these on my calculator because they're tiny calculations, but sometimes we get them wrong and then it gets frustrating. Okay, so negative 5 minus, and then negative 4. So I get negative 1 here. And then 4 minus 4 would be 0, so that's our lucky 0. And then 3 minus 4 is negative 1. All right, so we have one equation with 1 0 in it. Let's line up the row 3 with the same 0, because what we want is we want these two positions right here as zeros so that we can then subtract these two equations. And then another number won't pop up in these places. Okay, so we're going to do row 3. So negative 1 plus 1, we're actually going to add row 1. Okay, 3 plus 2 is 5. 2 plus negative 1. And then negative 1 plus 1 is our 0. 0 plus 1 is 1. So row 2 and row 3 are looking a lot alike right now. Okay, so we weren't able to tell in the normals, but take a look at this. If we take row 3 and we add row 2, okay, so what we're going to do is just write out row 1 and 2 as they are. Let's not change those at all. So 5 plus negative 5 is 0. 1 plus negative 1 is 0. 0 plus 0 is 0. 1 plus negative 1 is 0. As you can see right now, we have all zeros along the bottom. Okay, and I'm actually just going to multiply row 2 by negative 1, just so that these become positive. Actually, I'll do it here. 1, 1, 1. Okay, so now what do we have? What this actually looks like in equations is 2x minus y plus 1 equals 1. We have 5x plus y plus 0z equals 1. And then we have 0x plus 0y plus 0z equals 0. Okay, and we've seen this before. What this means right here is that it has an infinite number of solutions. And why is that? Because we can sub in any x, y, and z, and when we multiply the x, the y, and the z by 0, we are going to get 0. So 0 will always, equal 0. It'll always work out. So in this case, what we want to do is we want to sub in, let's sub in a parameter for x. Okay, so let's go x equals t. Okay, so this is a little bit different. We don't want to sub in a parameter for z because we have a 0z here. So I'm just going to sub in a parameter for x. Okay, which is totally okay. So parameter equals x, that will give us our equation for the last, for row 3. Now let's do row 2. So we have 5x plus y equals 1. Bring that over, y equals 1 minus 5t. Okay, so we have two of the parametric equations. Now row 1, 2x minus y plus, oops, this is 1z, sorry, plus z equals 1. So this is 2t minus 1 plus 5t plus z equals 1. Let's bring everything over. Z is going to equal 2t plus 5t is negative 7t on the other side, plus 2. So, therefore, the line of intersection, let's change color. Okay, therefore, line of intersection is x equals t, y equals 1 minus 5t, and z equals negative 7t plus 2. So there's infinitely many solutions that lie along this line. And you may get a different line if you subbed in the parameter like y equals 0, for example, or sorry, y equals t. So we subbed in x equals t. There's also the line when y equals t. It's just going to look a little bit different. And that's going to be the case whenever we get zeros along one entire row. Okay, example 3. Determine the solution to this following system of equations. So let's again take a look at the normals. Normal 1, normal 2, normal 3. 2, 1, and 1. 4, negative 1, negative 1. 8, negative 2, negative 2. So are any of these multiples of one another? Yes. The 2 and the 3 are definitely multiples of one another because n2 is a half of n3. So when we have a situation like this, we know that n2 and n3 are at least parallel. So if they're parallel, we could potentially stop right there because they're never going to touch. However, we need to know whether or not they actually lie on top of one another. Okay, so if they're coincident. So what we have to do is test the d values. Okay, so d2 is definitely 1/2 of d3. So the d values are the same. That means these two equations are the same. Okay. The situation that we have right now is that two planes, right? Pi 1 and pi 2. That's what I had in my head. Are going to lie on top of one another, and then it's going to be cut by another plane, and then we're going to have a line of intersection. Okay. We can see this using elementary operations as well. 2, 1, 1, 1. This is 5 and 10. 4, 8, negative 2, negative 1, negative 1, negative 2. Okay, so simply we can take row 3 and subtract 2 of row 2. By doing that, we're going to get all zeros in the bottom. This is just like the previous question. So let's go ahead and write 2, 1, 1, 1 across the top. Okay, so we can get this x value down to 0. So let's go row 2 minus 2 of row 1. Okay, so that'll be 4 minus 4 is 0. So that's our goal, so that's good. Negative 1 minus 2, I get negative 3. Negative 1 minus 2, I get negative 3. And then 5 minus 2, I get 3. Okay, and I'm going to take row 2 and I'm going to divide it by 3. 2, 1, 1, 1, 0, negative, oh no, I'm going to divide it by negative 3. So then we have positive 1, negative 1, and then zeros along the bottom. Okay, because we have zeros along the bottom, we know that this is the case. 0x plus 0y plus 0z equals 0. Any point is going to satisfy this. Therefore, we have a line of intersection. Okay, we have infinitely many intersection points. So let's sub in a parameter for either the y or the z. So let's just go ahead and go z equals t. Okay, so in the second equation, second row, we have x, no, we don't. We have y plus z equals negative 1. We have y equals negative 1 minus t. Okay, and then in the first equation, we have 2x plus y plus z equals 1. Okay, so I get 2x equals, well, minus t and t cancel out. Then negative 1 comes over. I get 2. X equals 2. Okay, so the parametric equation, switch the color again. Therefore, the line of intersection is x equals, y equals, z equals, x equals 2, y equals negative 1 minus t, z equals t. Sorry, this is x equals 1. 2 divided by 2 is 1. So sloppy. My mistake. Okay, there's our line of intersection. Okay, so again, it's two planes lying on top of one another, and then we have a line that cuts through it. What we're going to do now is we're going to talk about inconsistent systems, okay, for three equations representing three planes. So all this means is that there's like no point or line or plane of intersection. Okay, so case one, we can get a triangular prism. So none of the normals are scalar multiples of one another, okay? And if we actually drew these, or if we took a look at the three planes, they would form a triangular prism. So each pair of the planes intersect, plane 1 and 2 intersect, 2 and 3 and 1, but all of the planes do not intersect one another. Okay, case two, we kind of talked about this briefly. If two planes are parallel to one another, then immediately we have no point, line, or plane of intersection there. So plane 1 and 2 are parallel, and plane 3 cuts. So if you take a look here, plane 1 and 3 have a line of intersection. Plane 2 and 3 have a line of intersection, but planes 1, 2, and 3 do not intersect. Okay, and what we'd be looking for is that two of the normals are scalar multiples of one another. Meanwhile, their d's are not. So with their d's not being scalar multiples of one another, we would have parallel planes instead of the same plane. Okay, and then that third plane does not have a scalar, like a normal that's a scalar multiple of either of the first two. The other two cases where we have no lines of intersection or points of intersection are if the three planes are parallel, so all of the normals are multiples of one another, but then none of the d values are the same multiples of one another. Or if two planes are the same plane, so they're coincident, and then the third one is parallel. So those two planes have a scalar multiple of the normals and the d values, but the third one has a different scalar multiple for the d value. In this case, we would have two planes that lay right on top of one another, so they would have infinite points of intersection. They would have an entire plane of intersection, but meanwhile, that third plane is parallel and distinct, so it will never intersect the first two planes. Okay, so again, when we're looking at these questions, we're really approaching it from, do all three planes intersect or not? Okay, we can't just take a look at two of them. Okay, determine the solution for the following system of equations. So we have three equations, three unknowns. So first, let's compare the normals. Okay, 1, negative 1, 1. We have normal 2, which is 1, 1, 2. And we have normal 3, which is 1, negative 5, negative 1. Okay, so none of these are scalar multiples of one another. Okay, therefore we don't even have to check the d values. So let's go ahead and let's write 1, negative 1, 1, 1, 1, 2, 2, 1, negative 5, negative 1, 1. Okay, so I'm going to do two things in the first step. Okay, so I'm going to take row 2 and I'm going to subtract row 1, and that way we're going to get a 0 right here. And I'm going to take row 3 and I'm going to subtract row 1 in order to get a 0 right here. Okay, so row 1, doesn't move. 1 minus -1 is 2. 2 minus 1 is 1. 2 minus 1 is 1. Okay? -5 minus 1, I get -6. -1 minus 2, I get -3. And 1 minus 2, I get -1. Okay, so I have 2 zeros here. We can now compare these two equations. Okay, so just please note that all of the numbers in row 3 have negative signs. So what we're actually going to do is we're going to do row 3 plus 3 of row 2. So I'm going to write out row 1 and row 2 as they are, and then I'm going to go -6 plus 6 is 0. That's our entire purpose of this. Okay, -3 plus 3, well, I get 0 again, and then I get -1 plus 3, I get 2. Okay, so we've seen this before, but we've never seen a number here. So what this is saying to me is that 0x plus 0y plus 0z equals 2. So we've kind of seen this before, but if you think about it, any point that you sub in for x, y, and z is going to equal 0. So is 0 ever going to equal 2? No. What does this mean? This means that our system of equations is inconsistent. That means there's no point of intersection, okay? So let's actually think about this. We don't know whether this system of equations is a triangle. I don't even know how to draw this. Is a triangle. So since none of our normals are parallel to one another, so scalar multiples, we can say that there's no point of intersection, and these three planes create a rectangular prism. All right, example 5, let's determine the solution for this following system of equations. So normal 1 is 1, -1, and 2. Normal 2 is 1, -1, and 2. And normal 3 is 1, -3, and 1. So if we can take a look at these, normal 1 equals normal 2. They're not even multiples of one another, they're exactly one another. So our debate is, are these parallel? In the parallel case, there's no point of intersection. The third one's going to cut. Each of them individually have a line of intersection with each one individually, but all three planes will not intersect. Or option 2 is plane 1 and plane 2 are going to lie on top of one another, and plane 3 will cut it in a line, and therefore we would have to find the line of intersection. Okay, so n1 equals n2, so all we have to do is check the d values. Does d1 equal d2? No, they don't. One is -1 and the other one is 3. -1 does not equal 3. Therefore, these lines are parallel, but they do not lie on top of one another. Therefore, no solution. Okay, this system of equations is inconsistent. Okay, again, that means inconsistent means no solution. And we can just say two planes are parallel, and the third cuts through. So in this case, all three planes do not intersect. Okay, let's solve for this system of equations. Okay, so let's check n1, 1, 1, 1, n2, 1, 1, and 1, and then n3, I get 1, 1, and 1. This is beautiful. n1 equals n2 equals n3. So minimally, these three planes are parallel, okay? Or two of the planes can lie on top of one another, so pi 1 and pi 2, and the third plane can be parallel. Or plane 1, plane 2, and plane 3 can lie on top of one another. So we have to decide which scenario it is. But those are the 3 scenarios when all of the normals are scalar multiples of one another. So what we have to do here is check the n values. Sorry, the d values. So the d values are, well, technically -5, -4, and 5. So n1, no, sorry, d1 equals d3. Okay, so line 1 and line 3 are the same line. Line 1 and line 3. Take that back. Plane 1 and plane 3 are the same plane. Okay? Now, this does not equal D2. So D2 is just going to be parallel. The situation we have is right here. We have 2 lines that, or 2 planes that lie on top of one another, and then we have another plane that's just parallel. So we can conclude, therefore, inconsistent, no solution. Plane 1 and plane 3 are the same plane, but plane 2 is parallel. And we can say all 3 planes do not intersect. And that's it.